So pKa is a measure of how energetically favorable it is to add or remove a proton. Okay? And in this case, we're looking at, these are hemoglobin subunits, and what we can see here is we have a positively charged histidine side chain making an interaction with negatively charged aspartic acid. Okay? So our model pKa value from table 1011 were isolated amino acids in water. That approximately 6 was sort of this model value. Okay? Amino acids in proteins are not isolated, and they have a different local environment than just water. For example, here the histidine has some sort of local environment where there are other side groups around that it might be able to interact with. What its environment looks like generally has to do with some sort of electrostatics. And it can give us a very different apparent pKa value. And so what we're going to calculate is sort of the real-life pKa of histidine when it's inside of hemoglobin, as opposed to if it's this 6 value all by itself. So consider a histidine placed next to an aspartic acid in a protein. When the histidine is charged, it can make a strong, favorable interaction with the aspartic acid because they have opposite charge, so they can make an interaction. If histidine doesn't have that proton on and it's not positively charged, it can't participate in this. Okay? At biological pH of about 7, do you expect histidine to be protonated or not? I have both head shakes no and head shakes yes. How about from the previous slide when I was at 7 pH? Did I expect it to have its proton on? No, I didn't. That's what I showed. It looked like this. I said that from the previous slide, for a pKa of approximately 6 in isolation and a pH of 7, I expect 10 times more histidine without the proton on. Do I expect the proton to be on histidine in hemoglobin? I do. I want it to be able to make this interaction. If it can't make this, hemoglobin probably not going to fold the way it needs to, probably not going to behave the way it needs to. So I'm telling you, in isolation, in sort of a model system, I wouldn't expect at a pH of 7 for histidine to have its proton attached. In real life, not only is it attached, it's like 10 million times more likely to be attached. And we'll do the math really quickly. Okay. At pH 7, the ratio of histidine deprotonated without its proton on and with its proton on was 10. We can consider this the equilibrium constant. Okay, this is a reaction where there's only 2 things on either side. The reactant is histidine without its proton, and the product is histidine with its proton on. So just putting this plus sign here, this is attaching the hydrogen. Okay, so the reaction, you can write it as like his going to his plus. And at equilibrium, what I'm saying is from a macro scale, the concentration of these things, on a micro scale, the hydrogen's popping on and off onto a whole bunch of different histidines. Remember, we have moles and moles of histidine. It's not just one. But I could think from a macro scale, okay, it's not actually changing with time. This ratio is kind of the same. So I can set up products over reactants. So I can calculate a standard state free energy change for this reaction of putting the proton on. Okay? Change in free energy at standard state is equal to negative RT, the natural log of KEQ. So we proved this before at the beginning of chapter 10. If I plug in these values, go ahead for standard state. Let's use 298K here. The natural log of 10. This spits out negative 5.7 kilojoules per mole of histidine residues. So at a pH of 7, is it spontaneous to take the proton off? I think I said it backwards earlier when I was trying to set up this reaction. Where are all my markers? I keep leaving them in other rooms. So for KEQ, I have products over reactants, so I think I said this backwards here. This is what I'm trying to set up. It has its proton. I'm taking the proton off. Do I expect the proton to come off spontaneously? Yeah, it has a negative free energy change. If delta G is negative, I expect it to come off, right, based on this standard state setup and my model value for pKa. Negative delta G says the deprotonated form is preferred. And so that reaction would proceed forward. Okay. When histidine is charged and protonated, it can make a very strong, favorable salt bridge with aspartic acid. Delta G for that bond, the formation of this interaction right here, is negative 35 kilojoules per mole of aspartic acid histidines I have near each other in hemoglobin. Okay? What is the new apparent pKa of histidine in the folded protein? I want this new number here. pH is still 7 in the body. I need you to figure out, from a new value of delta G, get me a new KEQ, which will be this piece inside, and spit out for me what the new apparent pKa is, since I'm telling you 6 was not real life. And I'll give you this little hint here because I don't think anyone gets this step properly. In the folded protein, the charged form is stabilized by 35 kilojoules per mole. So for this reaction here, taking the proton off, it has two things contributing to delta G. It had this negative 5.7 kilojoules per mole, and then it has this actually, when it's going this way, turn this off. When I put the proton on, I can make a really nice bond with aspartic acid and release a big negative amount. But these two things have opposite charge, because in one case it's when the proton's on, and in one case it was when taking the proton off. So now that you have that bit for delta G, see if you can finish this calculation and get a pKa for me. I'm asking you for what this number really is in this scenario. It's not 6 anymore. Does anyone finish this one? What did you get?
12.
Anyone else get 12 for the new pKa? The right answer. All right. So I gave you delta G. I said there's sort of two things happening here. There's some spontaneous contribution for delta G in the forward direction for this reaction here. Protonated his taking the proton off. But I said when, in the other direction for that reaction, when the proton is on, that his would be able to make a really favorable interaction, a salt bridge with aspartic acid, that would contribute a release of 35 kilojoules of energy if it can make it. So my delta G in this sort of folded protein is competing between these two things, this negative contribution for sort of the standard state piece here, and then the added bit for what would the free energy change be when it can make this bond. So I have a new delta G to use 29.3 kilojoules per mole inside this folded protein for a histidine. So I have delta G, R and T are not changing, okay? I want to calculate a new equilibrium constant, a new ratio of deprotonated his to his for my reaction over there. I plug these values in, and I spit out 7.9 times 10 to the negative 6, a super, super, super tiny number, indicating that on the bottom, in an actual folded hemoglobin subunit, I would expect almost all of my histidines to be protonated. And if I want to get pKa, I can plug this ratio in here to the logarithm. pH was 7, I said, let it just be 7, we're in the body, and calculate the actual pKa value. This was pKa here. 12.1, that's what I got. The way to think about this, and going from 6 to 12.1, it's a 6-unit shift in a log scale, a 10 base log scale. It means we're talking about his being 1,000,000 times more likely to actually be charged with its proton in real life. That is what is being illustrated here.